My name's Waylon. I'm or Jepsen, one of the maintainers of Arbiter, and I'm just gonna give kind of a walkthrough of the architecture and kind of where the project's at, um, what it's been used for and useful for in the past, and where we see there being a lot of opportunity for tools like this moving forward. So you can see my screen okay, right? Awesome. Okay, so we kind of wanted my colleague is the other core maintainer right here. His name's Colin. Brilliant gentleman. Initially, him and I were looking to model the behavior of, at the time it was some DeFi stuff, different automated market makers, stuff with like constant function makers, and whatnot. And we had built some naive kind of Python simulations in the past. And while the Python simulations were like, good, and in some context, we found that they were falling short in other areas. So, for example, with the naive Python sims, you can generate a large quantity of data, which is good. Data allows you to bring a lot of insights. However, the quality of the data and the granularity of what the data was able to tell was not as good as we wanted it to be. And what we mean by that is we didn't have uh, execution parity with the EVM. And so while in like this Python environment, we were able to generate a large amount of data, we didn't have like actual execution traces. We weren't running real EVM bytecode on call data or deploying real smart contracts to Python simulations. So this is kind of like where a lot of the motivation to build Arbiter kind of came from. And so we decided to build around this project called Revum. If you don't know Revum, it's a really amazing piece of software. It's a critical piece of infrastructure used by a lot of remarkable organizations. Essentially, it's the Ethereum virtual machine instruction set architecture implemented as a stack machine in Rust. And it's actually, has been a core component of Foundry for a very long time. Recently, it's a core component of Ref. Um, we use it in Arbiter. It's also used in Helios and Zeth, of course, but definitely a critical component of the Rest Ethereum ecosystem. And so we were looking to build kind of an interface around Ref where we were able to have this kind of sandbox and granularity and being able to build super complicated, or not complicated, but like systems that had like a little bit more complexity, but were being modeled in a way that was as close to a production environment as possible. So the very first things that we did when we were building Arbiter is we built kind of a middleware around Revum such that we could make an object that had an externally owned account that could sign transactions, such as making contract calls or deploying contracts to our Revum environment. This has evolved over time such that we've built the Ethers RS middleware traits around Revum. So what's really nice about this, if you've been in the Rust Ethereum ecosystem, you've maybe used Ethers RS before. And a common object in Ethers RS is this middleware trait that usually is an abstraction. They call it the middleware onion around some functionality given at the end of the onion is a provider, and you send your EtherPC calls to the provider. And so we implemented this in this crate called Arbiter Core. First of all, we have three crates, and then we have some contracts. These contracts right here are not contracts you would ever want in a actually, you know what? I'll hit the contracts later. Let's go into the core first real quick. So first off, this middleware RS file is kind of, I'd say, where the meat of Arbiter's guts lies. And then we'll look at some examples at some point of how you might want to use Arbiter and how the CLI looks. And I can even give like a demo of what that might look like. So in this middleware RS, what we do, of course, we have a ton of primitives, and we also use this create the environment. Now, abstractly, we'll kind of just go through this line by line. I'll summarize what the environment is, and then we can look at the environment file if we like. But what's going on here is we are starting a Revum instance that will be continuously listening to, any in-memory interactions that our EOAs are going to send to the environment. So you can think of it as like an in-memory provider. What's nice about it is there's no, bandwidth constraints on port communication. You're not making like any actual RPC calls. What you're doing is you're just sending over a channel, over a thread in memory to your Revum instance to, interact with it as if you would an RPC, except it's in memory. And as a result, there are some trade-offs, but it's incredibly fast. You can see we have a benchmarks file here. We, wrote a little bit about this in one of the last blog updates, but essentially we have up to about 180 times as fast for stateful calls, and there's some other benchmarks for stateless calls as well. But the speed at which we can, run through opcodes and update the state in the RevMDB is really, really fast. And this is kind of a critical component of Arbiter. And without this speed, I think it would be a lot less useful. Okay, so the environment's kind of like this in-memory like mock provider where you send your calls to update things to. And then we have this Revum middleware struct, and we can see that it has this provider around this object that's a connection, and we'll see how the connection is defined. And then we also associate an externally owned account or a wallet here. So pretty simple. We have some custom errors here, general good practice, and if you're ever walking through this code, by the way, we spent a lot of time trying to document this really well. So our documentation on crates.io is, I think, pretty good. If you think it's bad or confusing, definitely open an issue. There's also an effort right now on some more granular documentation in an MD book that we're going to be working on after v0.6, which we'll be releasing early next week. That will have some additional features like forking state from mainnet, and also just some quality of life stuff, as well as some improvements to the binary crate and the CLI. But I digress. Our middleware errors, we can go through these if we want, but I think, yeah. Uh-oh. Let me see if I can. Oh, I think I was on the wrong tab. Okay, here we go. You can see this now. Okay, so I was just looking at this middleware RS. As you can see, docstring comments, everything's pretty well documented. We are working on an MD book to make it even better. This environment object is what I was talking about as having like an in-memory Revum instance that we kind of wrap a provider around and give it some broadcasters and some instruction senders, basically some different channels, which are, some nice different objects that, you know, standard in the Rust ecosystem. Then I was just talking about this Rev'em middleware struct, and this is what we implement the ethers middleware traits for. And actually, you can see here in the docstrings comments, there's some examples. So, you know, for example, if you wanted to create an in-memory Rev'em instance, what you do is you would create a new environment, and the environment takes some like configuration parameters. So you can determine like a hypothetical block rate that you would like to, you know, emulate, or hypothetical block time, and you can also determine a seed. You can also set some gas settings if you would like. And actually, a lot of this is going to get a little bit easier. The feature for the new 0.6 release is we're abstracting a lot of these parameters away to have some really simple default parameters, and we'll be using the builder pattern. If any of the listeners are familiar with the builder pattern, what you end up doing is you create something without any parameters. So you make a constructor with no parameters, but you allow yourself to have some setters. And if everything gets default parameters initially, in this way, the user has to do even less than this right here. And then we start the environment, so our like in-memory Rev'em instance is going, and then we make a middleware object, and we wrap it in an atomic reference counter. So this allows us to basically have multiple instances of it's an atomic reference counter is a smart pointer that keeps track of the amount of reference counts that an object has in Rust. So when you clone an atomic reference counter, you're not actually copying, you're just making a new reference. And this way, the Rust compiler, you know, is able to know from the number of reference counts when to drop the memory allocation for this object, which can help you deal with some, you know, ownership rules that might introduce some complexities around lifetimes. So here's how you would create a new middleware instance. Of course, Rev'em middleware errors. I'm not going to go super into these because I do want to be able to get through the things that are most useful to the listeners, whatever that may be here. So here's kind of some initial traits that we'll implement for the Rev'em middleware. We have some constructors, which we just saw how to use. As you can see, the connection is a bunch of channels right here. And these channels are basically the way in which a EOA, or the middleware, will communicate to the in-memory instance of Rev'em. Here we allow a user to manually update the block if they want to, or if they want to design some logic loop that they want to churn through and then update the block every X amount of whatever. We want to expose this API for whatever type of EVM sandbox the user wants to use. It's pretty standard. We also have get block timestamp, and then these are some Foundry cheat codes. If you're a Foundry power user, you might know a little bit about the Foundry cheat codes. We only actually put deal in this release, but we have all of the environment cheat codes in the next release that comes out next Monday, or we're shooting for next Monday, definitely next week. So by the time anybody would be listening to this, we'll have support for all of the additional Foundry cheat codes. We of course have, you know, an address that you can get the EOA's address if you would like, and we allow them to set the gas price of your simulation if you like as well. Now, this we're implementing the middleware trait, which is defined in Ethers RS as kind of like this standard interface for, you know, providers. that a lot of the Rust Ethereum community, if people have been in the Rust Ethereum community, they've been using this interface for a while. So we wanted to expose a similar API to our middleware objects so that it was something that people might be familiar using and that we were conforming to like the standards of the Rust Ethereum ecosystem. Now, I know that a lot of this is kind of in the midst of being changed with the Ethers rewrite with Alloy, and we definitely are going to be working to support that as it becomes more stable as well. I think in the next release of Revum, Alloy types are going to be supported, and we will propagate those changes downstream as the rest of the ecosystem matures. So essentially, when I was talking about this kind of onion pattern, every middleware has like an inner object. And this means you can like wrap different middlewares around each other. And maybe at the end of the recording, I can send an article. I think in the Ethers RS MD book, there's a page on the middleware onion and why they're using this pattern. So every middleware, everything that implements the middleware trait has an inner, and of course an error, and then a provider. These are kind of getters. Default sender is kind of the same thing as address. It's a little bit redundant in the API right now. But the real exciting part is, these send transactions. So right now, if you were to, use the Rust Ethereum ecosystem and make some calls to maybe a middleware around an RPC that you create, you're of course going to want to be able to send transactions. This is going to be sending any builded transaction with any call data. It could have create opcodes if it doesn't have a destination. It could be to a contract, in which case it's going to perform some execution logic in the contract. But this is kind of the standard way in which people build kind of a Rust SDK around the Ethereum RPC. And so, as you can see here, what we end up actually doing is we end up figuring out whether or not this is a create, like if there is a transact to, because if there's not a transact to, then we know this is making a create opcode. Otherwise, we know it's a call. Then we configure the transaction environment. We figure out what instructions we have. We have a set of instructions. We're making our instruction a transaction instruction. We're setting the transaction environment, and we're providing a channel to receive a result. So, when you make a call to an execution client, for example, usually you get a receipt back or you get some ETH logs. We needed a channel to be able to send these to, so we provide this outcome sender. And then, then we wait for an outcome, and when our outcome has completed, we build the success object with the reason, the gas used, gas refunded. We don't refund gas right now, so we haven't implemented this feature right now. But we do include the logs and the output, and a way to kind of like parse this unpack execution. We do a bunch of other stuff here. This is just if the outcome, we want to match our output on a variety of different calls that we could have. So if it was a create call, we're going to propagate our output with different information in the transaction receipt. Whereas if it was a call here, we're going to propagate a little bit different information in the transaction receipt. And so these are kind of the two that we want to match on. So this allows us to, have regular transactions that we send and deployment transactions that we send to Revum. Now, then we support the call, which are not state mutating. Um, and it will basically kind of do like a dry run. Um, so no world state change will be documented in our DB when we use the call as opposed to when we use the send transaction. So as you can see, there's kind of a collection, and we are actually improving the filtering right now in V0.6 as well. There's a collection of APIs here that should be familiar, and we're basically adding support for them over our in-memory Revim instance. Things like get block numbers, things like, create filters. Maybe you've used the filters to filter like, state changes and pools on, for example, like Uniswap. You can get the gas price, you can get the block number, get the balance. And this is kind of the standard API we have over our in-memory Revim instance. Now, there's a little bit of additional under the hood stuff here, but I wanna make sure I'm not getting too lost and that I'm staying on track and what I'm saying is actually useful and helpful. There are a few ancillary helper methods here. Something that's kind of cool, kind of a hack with this pending state is normally when a transaction is submitted to an EtherPC, it has a pending state. And what we actually do is we use a little bit of unsafe Rust, just like immediately mutate our pending state to resolved, which is why this exists here at all. So we basically gaslight the compiler and say, hey, you actually don't need to wait to be resolved because everything's happening in memory. You're not a real RPC call, so we're just going to resolve you immediately. Now, the other side, what's being transacted to, is the environment here. And as you can see, the environment, it has, a place where it receives instructions, a place where transactions are sent, a place where outcomes are sent, a place where outcomes are received. And these are the same channels that the middleware has as this connection object. So we look at the connection object, we have this instruction sender, and as you can see here, this instruction sender is a type alias over this sender, and the senders are from the crossbeam channels. So these are just crossbeam channels, so they're in-memory channels that we're just communicating back and forth on. So in our environment, we have the other ends of these channels where we can communicate from. However, we also have an EVM DB, some atomic state, some, handles for threads. So what we do is we do a little bit of multi-threading so that we allow the environment to be able to process as much as possible and not be blocked. We have some gas settings, our environment parameters, some custom errors as well that should be pretty self-explanatory, our constructor, but the main juice of the environment is this run function. And this run function is a little bit of a lot, but behind the scenes, everything that's being sent to our in-memory RevimDB is going to be handled inside this run function. So when we start Arbiter, we start this environment by running it. And when we run it, we step into some threads right here on line 358, where we're able to kind of listen to our channels and iteratively listen for transactions and process these transactions and update the EVM DB as we process our transactions. So here's an example of some of the transactions right now. Like we have some add accounts, some block updates, a single Foundry cheat code, call, standard call, a set gas price, a standard transaction. Remember, the difference between transaction and call is not state mutating, where transaction is. And then we have a variety of queries that can be sent as well. And what the run function will do is it'll process all of these and update the EVM DB accordingly. So in supporting something like this, what we've been able to do is give ourselves EVM execution parity by running like real opcodes and call data. So this is kind of the two main things, is this environment file and the middleware file. There are some supporting things in between these, but I think a lot of these are actually going to get cleaned up in the new release we're about to ship. So that's going to be pretty exciting. So let me maybe take a look, see if I could show you how you might use Arbiter. I'm going to see if I can change my screen to share a terminal. Let's just share my entire screen, see if this is... I'm going to actually go over the Arbiter binary real quick. So the Arbiter binary is just very simple CLI tools that just allows us to initialize a repository with Arbiter init, and then it has some abstraction around creating bindings. So when you create Rust bindings for a contract, under the hood we're using ForgeBind. If you're a Foundry power user, you're welcome to continue to use ForgeBind. What we've done is we've kind of wrapped some logic around ForgeBind so that we're outputting the bindings as a module inside the right place in the project directory. And then also we aren't generating bindings for ancillary contracts for things like interfaces or libraries or things we're not going to actually use directly. So what I'm going to do right here is I'm just going to do Arbiter init. And by the way, Arbiter is on crates.io, so you can do cargo install Arbiter if you like to grab the Arbiter binary. But I'm going to do Arbiter init and say example. I'm just going to call it an example. And what this is doing behind the hood is it's going to, I'm going to show you guys the template that this clones. It's going to this Arbiter template, and it's cloning this, and then it's initializing it with our name, our name that we gave it, and then it's generating the bindings for what's going on. So it's running bind on whatever the foundry.toml is pointing to being where the source directory for all the smart contracts are. So if we look, we need to go into example actually first. So if we look in here, we can see, can open up a VS Code instance. I can see we have some things. We of course have our workflows, we have our contracts. This is just the counter contract as an example. We have our source directory. With main, this is like boilerplate for how you can iterate on some very simple logic with just the counter contract using the counter bindings, which are generated right here. Essentially what we do is you create an environment, we start it, which under the hood calls that run function in the environment. Create some clients. We say, hey, create a client with this address. And then what we do is we send it to a deploy action, a deploy transaction with the counter contracts. We deploy the counter contract to our EVM sandbox here. And then I make 10 increment calls here, just for an example. And so actually what we can do is we can just run this for an example. If you know about Rust, the one thing that sometimes takes some time in Rust is the compiler. The compiler is incredibly powerful, but as a result, sometimes sometimes it takes some time, especially if you run it the first time. What's nice about it though is it does only compile diffs. So if I were to change something small in my main file, in my logic here, and run it again, it would only compile the diffs. So it wouldn't take as long at all. But what it's going to do, we should see, created client with address, counter contract deployed at this address, and then incremented 10 times, and then we read the call. So as you can see, this all ran in like less than like a second. So we now have the ability to interact with our EVM sandbox with like a huge amount of speed. And this might be a good time for me to maybe zoom out, maybe go back into this issue that I just made about the MD book that can talk about why is this useful, right? So we have this, EVM sandbox now. Like, what is the point of this? Is this even good? Why is this important? Like, so what? And I would say, okay, well, great question. Now, I think the first thing I would say is that there are a few things that become available to us to be able to model as, either security auditors, engineers and developers, or just scientists that before were not really possible to model at scale. And that's all due to the speed of which we were able to leverage around Revum. And so I think the main thing that you can do is anomaly detection here. And actually, we found a critical vulnerability in one of our contracts at Primitive. There's a tweet about it, and there's actually a vulnerability corpus here in the Arbiter repository, where as vulnerabilities are found with Arbiter, they will be documented. But the reason we were able to find this vulnerability, I'll just talk a little bit about how we set up the simulation. We deployed these some AMM contracts, our portfolio contracts. We minted some random tokens, and actually this is a really good opportunity for me to talk about these contracts. These were our random tokens we minted. And then we also deployed this infinitely liquid exchange. Now, this is never something you would deploy to the mainnet, but what it allows us to do is it allows us to feed stochastic price paths to a quote-unquote contract that can act as an infinitely liquid exchange. And thus, we're able to have an arbitrage actor listen to the prices that this contract has as we increment them, and then arbitrage to rebalance our AMM accordingly. And thus we're able to do some kind of stateful fuzzing across many different price paths to our AMM contracts. And this is actually how we found the vulnerability that we found in the portfolio contracts. And so if you are modeling AMMs, what you generally want to know is how they behave across different price paths, though, right? And so if you have huge amount of volatility in a price path, you want to be sure that your contract's behaving correctly given a variety of states that it could be in or might be in given prior market conditions. And so we use stochastically generated price paths to do this. However, you can, if you want, also use historical price paths from ETH mainnet to model things in the same way. Under the hood, Arbiter, re-exports a library called RustQuant that generates any amount of stochastic processes that you want. We primarily have used them for price processes so that we can iterate over like, hey, there's going to be, let's do like 25,000 swaps. So we're going to have 25,000 different price updates. Maybe we want geometric Brownian motion. Maybe we want mean reverting price paths. Maybe we want jump diffusion price paths. And then after every update, we can, see somebody swap our agents. We can simulate a swap. Um, and then with real EVM execution parity, understand how the system evolves over time and look for anomaly detection. Now, one thing that's cool and kind of important is that you don't have to just model DeFi. We, of course, started modeling with DeFi, but you can model any EVM contracts and any agents that might want to interact with those contracts as they would in a mainnet environment. So, for example, right now, I'm working on modeling Optimism's fault proofs. Um, it's really important for Optimism's fault proofs to work really well. And so I'm working on modeling them. And in the fault proofs, there's a game played called the dispute game, uh, where you always have an honest actor that is disputing an honest execution trace, but also a variety of dishonest actors. And for the dishonest actors, you might want to use some random sampling for anomaly behavior to iterate over many thousand times to try and statefully fuzz the system so that you can look for anomalies, edge cases, or vulnerabilities. So does that all make sense, first of all? I just gave a lot of information, and I just want to know if there's any questions or if anything is not super clear or if I just blatantly neglected to elaborate on something and assumed too much credit. Yeah. This Yeah, so this is all so Arbiter right now is a Arbiter core is a library. So we're just using the Arbiter core to bring in an in-memory Revum instance that we create with this manager and add environment and start environment. All these lines right here, 16 through 22, are basically creating an in-memory Revum instance and and then this line right here is giving us the Revum middleware object in an atomic reference counter. And so now this as in its constructor takes an environment that it wants to be connected to. And remember, these are communicating over some channels. And so now this middleware is connected to this in-memory instance of Revum that's running. And that's why we're able to send a deploy transaction to it in just a few lines of code. We don't have to manually build the transaction if we don't want to. And this API comes from the bindings. So if you use forge bind, these are basically an abstraction over the Solidity contract in Rust that allows us to interact with these. These are auto-generated with forge bind, which uses the Ethers RS ABI gen under the hood. These are currently using Ethers types. It is in our interest to figure out ways to migrate these to Alloy types, and it's also in the Foundry team and the Alloy team. Everybody's working on migrating to the Alloy types. But yeah, this is pretty nice because now all we do is we do OK counter deploy, and then we pass in a middleware object and then some constructor args. We don't have any constructor args for the counter. So if we look here, there's no constructor. And then we await that asynchronously, and boom, we get a deployed address. And this is being deployed in our in-memory instance of Revum, yet again, as this environment. When you start the environment, you start the run function. But as I said, this will actually even be less lines of code in the future. Next week in the release, we simplify this even more, make the end user API even easier and simpler, so that our goal is that it's very easy to write a Rust program that uses Arbiter. Um, we are actually very open to listen to community feedback. If you have questions about Arbiter, join the Telegram. There should be a link, I think, right here. It might not be. That might just be a tag on Primitive. Reach out to me on Twitter if you can't find the link at 0x Jepsen. Happy to send you a link, get you in the Telegram. Or if you want, just open up a new issue. We're super receptive to any people in the open source community and what they want to use this for. Um, we've had a lot of support from different auditing firms that want to, use this, which is wonderful. And I think we're in an exciting time where people are actually using this to audit their contracts for, economic mechanism design, but also, regular contract anomalies. There are some people from academia that just want to use this to model things. Um, so there's a large array of people interested in using this, which we're super excited about. As a result, we want to make it really easy to use. So if you have anything that you're struggling with or anything that's not clear, open an issue, reach out to us. We're super happy to, address that issue, ship that feature that you want, or answer any questions that you may. So does that make this example super clear? Um, and if so, I can maybe talk about how you might go from here given other contracts that you have. And we can even pull up some more complicated simulations if we want to go over maybe a more robust utilization of Arbiter. Awesome. So here's a more complicated example. This one also is open source, and it should be very easy to replicate on the Primitive Finance GitHub. Essentially, this repository should just be called the Portfolio Simulations, and this is actually the simulation that found the bug. And as you can see, we're on the reproduce bug branch. Yeah, is that better? Should I do more? Okay, nice. So yeah, what we have here, we built some logic to parse a config file. And so if we zoom out, we have this config toml. So this config toml has some environment parameters, some gas settings, a label, and then also some parameters for whatever price processes we're going to be running. Some constructor parameters for our tokens we want to create, our pool parameters for the pool that we want to create, some stuff for the LP types, and some number of price paths. Now we can increase this to, parallelize this and make this go really fast if we want, but let's just start simple. We also have a timer we made and a logger that we initialized. So we parse all this configuration, this config file, and then we iterate through particular configs. So this parses into a vector of configurations. So we're now for each, configuration, let's, create a thread and run that simulation in that thread. And so that's why we create this vector of join handles to keep track of all of our thread handles. And we grab our seed here. Now we sweep over the number of price paths that we want to do, and for each price path, we grab our configuration parameters. These are the constructor arguments for our tokens. These are the constructor arguments for our environment, the pool parameters, and the price process parameters that we just saw right here. If there's a seed, we initialize our seed. The seed is kind of important when running simulations because something that's really important is reproducibility, um, which my I had to learn from my colleague. Actually, I didn't think the seed was as important as it actually is, but it is very important. And then we create a new handle where we, create the manager, the admin, and the arbitrageur with this helper function called initialize. And we can look at what this one does. It's in startup here. Essentially, we are going to return a simulation manager and then two clients. Of course, you're familiar with these lines. They're in the same exact um, we just looked over the Arbiter template. And we're creating an agent called the admin. They're going to be taking care of things like deploying different contracts, minting tokens, stuff like this. They're also going to be updating the stochastic price process. So we create an admin agent, which is just an atomic reference counter over the middleware. Remember, each middleware has an externally owned account. Then we create an arbitrageur. This is the EOA that's going to be executing the swaps and rebalancing the pools. And then we basically return the admin, manager, and the arbitrageur. So if we go back to the main, that's all that's happening right here. Then we're going to deploy contracts. So we have a helper function here that's going to be deploying our different contracts. So we're going to be deploying two tokens in the liquid exchange contract. We're also deploying the WETH contract. WETH contract is, I believe, actually the WETH bindings are native in the Arbiter library, so you don't have to create them yourselves, as well as the dummy token and liquid exchange contract bindings. So don't worry about generating those yourself. Those are in the Arbiter core lib. You can always import those. So we deploy a WETH contract. We deploy an Arbiter token. Then we deploy another Arbiter token. So we need two tokens for a pool. Then we deploy the infinitely liquid exchange. Then we deploy the portfolio contract. And then we actually have this contract here that essentially is a multi-call. It gives us some atomicity for our swaps. We call it a normal strategy. Then we deploy something called an Arbiter math contract. So this is just for performing on-chain math operations, stuff from Soulmate and Soulstat, just kind of to make things fast. And here's our atomic arb. Actually, I think the normal strategy is not the atomicity, so let's take a look at it, actually. I think it's in our lib. Yeah. So I believe that our normal strategy is basically pool configurations for a stable pool here. So what we're doing right here is configuring our constant function in the AMM to basically have a normally distributed liquidity around a specific price, where in this case our price is 1. So that's why we're calling it the normal strategy here. So if you know about the trading function we play with, it came from the replicating market makers paper that Trun and Guillermo published about 2 years ago, maybe 3 at this point. Wow, time flies. And it allows us to allocate liquidity in this sort of normal distribution around different price points. And sometimes this liquidity is time sensitive. So sometimes as a pool reaches expiry, liquidity will concentrate more, whereas upon pool initialization, if it has a long expiry, it would have been wider distributed, if that makes sense. So we deploy this pool, then we deploy the math and the atomicity contract. This is kind of like, you can think of it as like a bundler of some sorts. And then we return all of these contracts. Okay, so far so good. Any questions? Am I good to keep going? Or are you incredibly lost? Does this all make sense? Okay, no. Yeah, so essentially we have all of our contracts that we deploy. Um, of course, we have to await that since we're making calls to our in-memory. But this uh, is asynchronous, but it won't like take time. It's also only asynchronous in this thread. So for each price path, each thread is doing this. Um, then we do our allocation and approval. So as you imagine, some initial things we have to do to get to the state of the EVM is we have to give people some tokens. So we have to mint some tokens. We also have to do token approvals. If you've, played with token contracts before, you know that this is something you got to do. So we pass a client for our arbitrager and our admin, our two token addresses, our infinitely liquid exchange address, our portfolio address, and our atomic arb address. And essentially, this helper is just making approvals and mints for all of these contracts. So we're iterating over our token contracts, and then we're minting for each contract. We're minting to the admin address, we're minting to the liquid exchange address, and we're just minting the max U128, and then we're minting, and then with this one we're just actually approving to the portfolio address. Now we're giving the arbitrager just one token, the Y token. Then what are we doing right here? We're looping over tokens that have the arbitrager client and approve the liquid exchange and portfolio contracts on behalf of the arbitrager. So these are token approvals right here. We can see we're using the approve method of these contracts. So we're approving these tokens to the liquid exchange, portfolio address, and atomic arbitrage address. And these are all for the arbitrageur. Okay, so mints and token approvals were the next thing in our list. That's what we did right here. The next thing we do here is initialize the portfolio pool. Oh, and by the way, since this is the same API over like the middleware API, this is also a lot of the similar types of things that people who are searchers that manage predominantly off-chain bots do. And actually, a lot of them do it with the Rust Ethereum ecosystem because if you know anything about Rust, it's very fast. And when you're searching, it's very important to do this. In fact, one thing we've been thinking a lot about and playing around with in a number of different sims is using the Artemis framework inside of our simulations, where the Artemis framework is the, MEV framework developed by Frankie at Paradigm, where essentially you have executors, collectors, and strategies, where your collectors just collect events from the chain and turn them into different, Artemis events, and then the strategy takes these Artemis events and decides whether or not to act on them or not, and if so, what transaction do you build? And then the executor, of course, sends those, whether atomically or not, to the blockchain. So it's kind of a cool abstraction over talking to the blockchain, and we're definitely still investigating how to use it inside the simulations as kind of a cool framework for us as well. Okay, so we initialize the portfolio pool. This right here, we pass portfolio, normal strategy. These are both middleware objects, references, portfolio pool parameters. This comes from the configuration file, if you recall earlier. An asset address and a quote address. These are addresses of our two tokens, and then an LP address as well. If we go back, we can see that our LP is just our admin here. And then what we do in here is we call the create pair call of the portfolio contracts. So we want to like go look up to the portfolio contracts. Where do we have that? Oh, I think, give me a second. I think this is the interface, but I think we can grab the same thing. Create pair right here. So it basically adds a new pair to the portfolio state. What it does is it takes in two tokens, and then it emits this event with the pair ID, the asset, quote, decimals, and the quote, decimals of the asset and decimals of the quote. Then we get the pair ID, which is just a read call. So these are non-state mutating calls. We log the pair ID, and then we create our strike price based off of our config file. So our trading function takes in a strike price as one of its parameters. Also takes in volatility parameter in terms of basis points, and then durations in seconds. So if you're familiar with finance, this is like strike is K, sigma is volatility, tau is duration. And we grab an initial price that we want to initialize our pool at. And then we call, this is just a read call, we're just grabbing strategy args, reserves X per wad, reserves Y per wad. So this normal strategy function right here is being called on this contract right here. And we're calling get strategy data. Let me see if I can find the interface. What's the difference between these two? Yeah, one's the lib. Get strategy data. So we're calling this function right now, and we can see the documentation for this right here. Takes in the strike price, volatility basis points, is perpetual. So we have a kind of a indicator of whether or not we want the pool to be perpetual or not. The initial price to approximately set the pool to. Strategy data is the config is that it's going to return, and that's what we're getting right here. So we're taking in these three things, and we're returning the strategy data. And we're basically doing this because we're going to pass the strategy data to create pool. So if we go back here, that's why we're getting the strategy data. We're deconstructing the strategy args and the X reserves and the Y reserves. So we go back here, strategy data, initial X, initial Y. It's read functions. We don't have to say send. We can just say call. And then we build our create pool call object here, which is basically going to have all of this information. Some of it, at the end, we get the strategy args as bytes. Strategy is just the strategy address. Controller. These are for managed contracts. We're just kind of setting these to defaults right now because they're not super important in our simulation. But you certainly could set these to things if you want to simulate managed strategies or active strategies in whatever, smart contract system you're building. We have our priority fee basis points and our fee basis points. So in our trading function, we had a priority fee and a fee. So we were, experimenting with things like LVR, mitigation mechanisms with priority fees to our pools, which is a rabbit hole, so I won't go like too deep on that, but we were wanting to essentially host our own MEV auctions at the application level to migrate a lot of the value for priority swaps to the LPs. So there was some things we were playing with there. So we create the pool. We get the create pool log. We deconstruct the create pool log, and we log it we log the pool ID. We make our allocate calls, allocating on the behalf of the admin. So this is depositing into the pool, and then we're getting the initial pool reserves. This is just create pool filters. Otherwise, we wanted this is kind of error handling. Like, hey, if we didn't get that create pool fill event, then, something went wrong. Okay, so we're almost to the main event loop where we run our simulations. Setup is almost all good. Initialize portfolio. We create our price changer. Our price changer is basically going to be the admin's communication, which is the admin's middleware object around this liquid exchange, and our price process parameters. So the admin's going to basically be feeding this contract new price updates that it's going to report, which are going to be emitted in events. Then the arbitrageur is going to be created. The arbitrageur constructor takes in a liquid exchange. Now we already have one that's deployed, so what we're doing is we're just giving it an interface that's associated with the arbitrageur EOA right here. Same with portfolio. We're passing it the math contract in case it wants to do any solstat or soulmate math in a separate thread. We're passing it an atomic arb contract that's associated with its address, and then giving it some portfolio pool parameters and the pool ID. Now we're basically going to be logging a bunch of data from the simulation. So for example, we're going to be wanting to getting the balances of the arbitrageur, the balances of the pool, how they're changing over time, all indexed at different price updates. All of this data is really useful and valuable. So we built a structure that has an interface called update output to log a bunch of this information. And then we run the simulation. And this is essentially it. This run function is, about 100 lines long, but this is the loop that loops through the prices that we in our price process, updates the price, computes the swap detection, and our arbitrageur has a detect arbitrage interface where we do the AMM math, and this is where we make calls to the, separate math instance to do things fast if we want. And then, based on the swap direction, we execute arbitrage. And then we, log the price that the pool reports after the swap. We log the reserves after the swap, and then we update the output, and then we do this again. And we just churn through this maybe like 20,000 times and look for different anomaly behavior. So I know that that was a lot of information, and I, kind of glossed over some information like, oh, what does the detect arbitrage interface look like? But this is in general, 100 lines. The setup was a little bit verbose. We have about 300 lines of code that are used to configure the initial state of the simulation in our in-memory EVM instance. And then we have about 100 lines of code in our run function, and that's our simulation. So you do definitely have to be familiar with Rust. This is definitely a tool for advanced auditors or power users right now. We would love to make it super easy for people to use and are always working to make it easier to use. But this is a very powerful tool, given that just a few hundred lines of code, you can do such robust stateful anomaly, stateful fuzzing and anomaly detection on with real EVM execution trace parity. But yeah, are there any questions on that? How was that? Does that make sense? Any questions? Was this example helpful? We will be adding more and more repositories or examples, and there are a few users of Arbiter that have open source projects where they use it to simulate things as well, and we're always highlighting their work whenever we see them do great work as well. Yeah, this one, the portfolio AMM is very not like a simple AMM to simulate. But in general, if you want to simulate an AMM like this with Uniswap, would be a lot easier too, because the pool initialization on Uniswap's easy. Oh my God, I'm so glad you asked. So we're always trying to, make things approachable. One thing that I think a bunch of different contributors are interested in working on kind of together, and if anybody wants to do this, they're welcome to work on this as well. But we're working on putting together an MD book for the repository so that there's some more detailed documentation on how to use the library other than just the create stocks. I drafted kind of an outline here of what I think are important things to touch on. I kind of have three main sections here: auditing, contributing, and kind of introduction and getting started, I guess four. And I did also reference the Revum MD book, the Foundry MD book, and the Ref books, which are all quite good. I'm most familiar with the Revum one because I worked on that one a lot, but they're all quite good, and I think that all of these topics are probably good things to highlight and illustrate. I think there's a lot of opportunity using Arbiter for auditing, actually, in particular. I think that auditing is super, lucrative for anybody in the industry, and I think this definitely, using Arbiter gives you a huge edge to audit, and the vulnerabilities we found were vulnerabilities that some of the best auditing firms missed. We had a lot of audits on the portfolio contracts from organizations like Trail of Bits and Spearbit, and we think those teams are top notch, and it was a pleasure working with all of our auditors. And because they were so top notch and miss some of these vulnerabilities, I think is a testament to the power of the tool. And I think there's a lot of opportunity to find tools. But if you want to work on this MD book, I think this is a great first issue to start. I know Sabnock put together just this morning, I believe, just the architecture. So if you want to make a pull request into this branch, or maybe I'll merge this and we can talk in the Telegram about what's the easiest way for people to contribute to this. This is just an empty MD book right now that just has all the sections and subsections that I recommended. But I think writing documentation is a really good way to familiarize yourself with a code repository that you're trying to learn, trying to use. It's actually why I worked on the Revum docs. So I was like, okay, I really want to understand Revum to a much higher degree because it's the primary core dependency of Arbiter. So that's something that I think is really helpful if you're looking to get involved and contribute. I also think if you are a smart contract developer or an auditor, um, try to use the Arbiter CLI and deploy some contracts. And once you have some contracts deployed, see if you can build an EOA to talk to them, and maybe do it in an algorithmic way where you can leverage Revum's speed to talk to it in a way that allows you to find anomaly behaviors of the contract. And if you run into anything, definitely, like I said, reach out. Arbiter is kind of my full-time work and my lifeblood and my child. And so if you're using it and you're struggling, let me know. I'm happy to troubleshoot your problems with you. And if it turns out it's a bug, I'm so glad you found it. And if not, how it was challenging and unintuitive to solve the problem you were working on helps me and the other Arbiter maintainers build a better interface. Yeah, I'll send you a link to the Telegram group. Awesome. Yeah, let's stop recording and then